Hi, welcome to this lesson on calculus, finding tangents to functions. Let's have a look at equations of tangents to a function. So to find the equation of a tangent line to a function, we need to know the general formula of what a tangent line is. A tangent line is a straight line, a linear function, and can be represented as y equals mx plus c, where m here is the gradient of the straight line. So if we have a look at this function here, then at a point on the function f, let's call it a, and then f of a is the y value, then the tangent line that meets at that point there will have a gradient m that is defined as the first derivative of that value a. So the gradient of a tangent line is the first derivative at that point a. Okay, so that's really, really important when we go forward. So the equation of the tangent at that point is given by y minus y1 equals m times x minus x1, as we saw for the straight line properties, where a is the point a f of a, and your gradient m now is f prime a. So if we substitute these for your points y1, x1, and m, then we have y minus your y1, right, in this graph. So here's your x1, y1. Your y1 is f of a equals your gradient now over here we saw is the derivative, first derivative at a, times x minus x1. Your x1 is a. So if I take over this f of a here to the right hand side, I get this formula now. So this formula here is the equation of the tangent line. So your tangent line is the derivative at a times x minus a plus f of a, where the point a is given by little a, f of little a. So, in general, to find the equation of the tangent line at a point a, f of a, on a function f, we only need to know the first derivative at that point, right? And that'll be the gradient of the tangent line and that point that we have. So let's have a look at a concrete example to apply this. So we want the equation of the tangent line of the function f of x equals x squared at the point 1, 1. So here's the point 1, 1 on f of x equals x squared. All right, so if we draw a tangent line here in purple, the gradient of that tangent line is going to be the first derivative evaluated at x equals 1. Okay, so if we do the derivative of x squared using the power rule, we get 2x. And then if you put in 1 for your x here, so f prime of 1 is 2 times 1, which is 2. So your gradient of your straight line of the tangent is 2. So this gradient of the straight line here is 2, so 2x plus c. So if we can find the value of c, then we are done. Then we've got the equation of the tangent line. Okay, so to get that, we'll substitute the point of contact, which is 1, 1, into the equation. So this is your y equals mx plus c. So I put in y for 1, x for 1, and solving for c, I get negative 1. So that makes sense. If you look here, it cuts the y-axis at a negative value. So this is the 2x minus 1. That is the equation of the tangent line at this point here. All right, so what does this mean? Again, in terms of context of differential calculus, it's saying that the rate of change of the function x squared at the point 1, 1 is 2. So it's changing in a positive direction, a positive 2. That's increasing essentially. And if you look up here, the graph is increasing in that neighborhood there. All right, but we'll look at that when we look at the first derivative applications, where we look at intervals of increasing and decreasing as well. All right, so that is the equation of tangent lines to functions. Let's have a look at some examples. I'll see you in the next one.